So I'm sure you're all aware the LO2 checkpoint is up ahead, is upon us. So if you're still finishing up point of sale, make sure you get that done soon. As long as you show good progress, you have effort shown on it, especially if you did the prep lab and everything, you're almost certainly going to get the deadline extension. So if you're not done with it at like midnight tonight, keep working on it, keep plugging through, because you'll almost certainly get a deadline extension. Unless, the students who don't get deadline extensions, the first extension at least, they're the ones who make their first submission today and have no evidence that they've even thought about the assignment until right at the deadline. Those students might not get extensions. But if you're working on it, keep working on it, keep plugging through, and get the lecture tasks done. Substitute Dragos. What happened to Dragos? Yeah, lecture attendance is looking pretty sparse, which, if all the empty seats have to fail the class, you know what? I'm not going to babysit. So let's get into lecture content today. Today is demos. I want to show some demos of things that we were talking about. I have lecture task style questions that I'm going to work on. I'm going to spend the whole lecture in IntelliJ and show you examples. This is meant to be interactive, so if you do have questions, especially if I'm going too fast, if I'm blazing through things and you're like, whoa, what did you just do there? Make sure you either shout out, raise your hand, hit up the lecture channel on Discord, I got it right here, and say, what was that? I'm doing this to show you, to help you as you approach your lecture tasks. So if it's not meeting that end, let me know. Let me know what I can do to make that easier. I just want to show some examples of applying the concepts that we've been seeing to make it easier when you're actually heading into the code. So with that said, I only have a couple of slides. I'm just going to introduce the questions for immutability, but I'm also going to do recursion. All the solutions today are going to involve recursion. And we're going to rehash testing. I'll spend probably more than half of the time in the test suites in the code. But let's get into it. So the lecture task today is to write a score function for your song class. So how do we rate a song? How do we score a song? Which will end up being the score that we use for the genetic algorithm in application objective 1. So I won't go through all the rules here, but this is the structure of rating a song based on not only all of the ratings from all the users, but also the ratings of a particular user. We want to know how likely is it that this particular user is going to like this song. So specifically, if they rated the song, if they gave it like a 1 or a 2, we're going to say, well, we know they don't like the song. If they gave it a 3, 4, or 5, then we're going to take those numbers and then combine them with the average rating, the Bayesian average rating for that song, and decide how much this user will like that song. So the examples today, I'll introduce both of them in the slides, and we'll head over to IntelliJ. So the first one, I want to write a method named histogram that's going to take a list of integers and return a list of integers to integers. The returned map is going to be a histogram where the keys are the integers that appear in the original list, and the values are how many times that particular integer appeared in the list. So we want to take a list of ints and return a histogram. How often did each int appear in that original list? And then test that in test histogram test suite. The next one is going to be a number guessing game. We want to simulate the game where you go, I'm thinking of a number between 1 and 100, and then somebody guesses the game. You either say higher or lower, and then the user eventually guesses that exact number. So we want to build this number guessing game where we're going to automate the guessing. We're going to give it a function which is going to say higher or lower when it's given a number. It's going to return a Boolean. It'll return true if the number to be guessed is higher. So true is going to be higher and false is going to be lower. And then our method should guess according to that answer, according to that oracle, according to that function. And these will be doubles, not just ints. So we have to return the right answer to within 2 decimal places. And all of this without using any vars. We're not going to use any vars today. Which brings us back to the lecture test, and the slides are over, so let's head over to IntelliJ. And if we do have time, I'm going to add a third method, this most frequent. Hopefully we'll have time to get to that one. I have a lot of the structure set up, so you're not just watching me type boilerplate code, and then I want to talk about the interesting stuff. So the first thing, I went into my code, and this is the first thing you should do with any lecture tasks or application objective. Go into the code and just create a stubbed out method for that task or objective. So here I created my object, in my package, created my method, and then every task specifies the input and output types. So I'm going to write a method with the appropriate name, a method named histogram that takes a list of ints and returns a map that maps ints to ints. And I'm going to stub it out. When we say that, when I say that, I mean just return anything, any value that doesn't cause a compilation error. So I'm going to return an empty map here. We'll eventually write this method. But I want that structure so I can start writing my tests. Then when I go into test histogram, I can call that method without getting an error. Because if we try to test that method before it even exists, it's going to give us all kinds of errors. We're not going to be able to even write our test suite. So now we have our stubbed out code so we can write our test suite. Just like you've been doing in the prep labs, you'll create some stubbed out code and then write your test suite based on that stubbed out code. And then once your test suite is complete, then you'll go and implement the code. This is called test-driven development, and we're going to embrace test-driven development here. We'll write our tests before our code and use our tests to help us write the code. It makes writing the code significantly easier if we already have a test suite ready for it. If we don't have a test suite, how do we know our code's right? We're just guessing at that point. We're going to submit to Autolab, wait till Autolab says our code is good, and then write our test suite afterwards, and then let Autolab decide when our test suite is good. We don't like coding like that. We're going to write our tests first, think through our test suite, get a really solid test suite, write our code and keep running our tests against our code until that really good test suite passes our code, and then we're feeling really good. Then we submit to Autolab. We should only have to submit once per task or per objective. And Autolab should just be like, oh yeah, this is all solid, because you clearly did a really good job on this. So for my test suite here, for testing histograms, I'm going to put all my test cases in a map like I like to do. I'm going to map inputs to expected outputs. And I have one test case here, just that I set up before lecture just to get us started. An empty list should return an empty map. If I don't give it any values, then I should get a map that isn't a histogram. I mean, it is a histogram, but it doesn't have any data, no keys, no values, nothing happening. Then I'm going to iterate over my test cases, call the method I'm testing with the input, and then check it against the output. So let's get at least one test case here, one meaningful test case, and I'll create, I don't know, a list of 1, 1, 2, 5, 5, 6, 6, 4. Oh, I shouldn't have made this so big. Now we got to really count these things. And then I'm going to map to a map. I have 3 1s, 2 2s, 1 4, 2 5s, and 2 6s. So that's my histogram for this input. One big reason why we like to write the test cases first is it forces us to fully understand the input-output behavior of the method. If I have a list like this, I have to think about everything of what I expect the method to do when I write this test case. If I have this input list, I'm going to count the ones. There's 3 of them, so I should map 1 to 3. That part of my histogram, 1 appeared 3 times in the input list, so that part of my histogram, that key value pair in my histogram should be 1 to 3. And then so on, then I just count the number of 2s. This is a mistake I'm still seeing at this part of the course. You should be hard coding your test cases. Like actually go through and count the values and then generate your test cases by manually figuring out what the expected output should be. and hopefully I did all my math right here, and manually figure out what the output should be. I see a few mistakes. The biggest, most crucial mistake, which giving feedback to students who unfortunately failed after pale blue dot, of using their own code to generate your test cases. If you're using your own code to generate your test cases instead of computing them by hand and manually figuring out what the expected output should be, it's just a recipe for disaster. You're completely eliminating the whole point of testing. If you use your code to generate your tests and then your test to verify your code, you're not verifying anything because the code's just verifying itself. No matter what your code does, no matter how wrong it is, it's still going to pass your test cases. And then you submit to Autolab, and Autolab says your test cases failed the correct solution, and you don't really have anywhere to go except starting over and actually generating good test cases. So a word of caution, if you made it this far in the class, you probably haven't really made that mistake, or you've just gotten lucky and your code was actually correct, so you were able to generate correct test cases with your code. You're not always going to be lucky with that. You are playing with fire when you do that. I know students do it because, it saves time. If your code is correct, it does save time. If your code's not correct, oh my goodness. So we want to manually verify our test cases. This gets tricky, like with this one. With this problem, it's not too bad. It's designed so I can actually do it during a lecture in a 50-minute confined time limit. But if you have, let me just generate a few more test cases while I'm talking. -4. So sometimes it's much harder to generate those test cases. For LO1, when you're going through the cities.csv and trying to manually come up with test cases, I always recommend to find a country with just a handful of cities and then using that country for your test cases. But it does get harder. It does take a while to generate test cases in a lot of cases for a lot of problems. So here I'll have another test case. I have a list with just 4 values of the same value, and I'm going to start throwing in different things. I'm going to really challenge my code and test my code to make sure it's going to do what I want. So I have 5 values that are all the same value, and it's going to be a negative number to make sure my code's not doing something silly on negative numbers. Let me do the same thing, but right in the middle, I'm going to put a 0. Zero to 1. There we go. Let me just do one more test case. I would want like 10 or so at least test cases here, and test cases that are very different from each other. If you have 10 test cases that are all basically the same, it's not really testing anything. So let me get another test case that's, let's see, -1, 0, and 1. Make sure I'm not handling -1 and 1 the same way. -1 has 1, 1 has 1. I don't want to do too many in lecture just because it's boring watching me do this. Let's do another one with like a little mixed up order and a couple of duplicates. 2 of these, 2 of those. And we should feel okay about that. That's not a terrible test suite by any means. It would probably be fine for, if this is a real objective, that would probably get all of my incorrect solutions for this course, which doesn't necessarily mean it's a solid test suite. It just means it was good enough for credit. And I'm going to run this and watch it fail my code. So the output I'm going to get, map, did not equal this map. Here's my first quiz question for you. I'm using equal right here. Can I get away with this? Is this a proper test suite? Is that equal going to be good for me? Is it going to do what I expect it to do? Jeez. What's that, 57 people? I assume that's in the point of sale document. Yeah, everybody's doing the assignment right now. Yeah, project 2, point of sale. Goodness gracious. I'll oof that. So can I get away with equal here? Anybody say yes? Anybody say no? A couple no's, a couple yeses. I'm going to say, I would like to quiz you and hear from somebody, but, in a large lecture hall, that's a little tough. I'm going to say we can get away with this one for a few reasons. So maps, if you look at this map here, it's going to be 5 to 2. It's going to be this test case right here. It's going to be this expected output. But notice how I entered these in order of increasing value of the keys, just the way I happened to write it up because I didn't want to miss a number. But when it's printed here, it's not in that order. This is our daily, not daily, but monthly at least, reminder that the order of the key value pairs in a key value store in a map in this case don't matter. There's no concept of ordering here. So it doesn't matter which order I put them in. So it's not like lists where we had to worry about sorting the lists. And since these are all integers, we don't have any doubles in this problem. We actually get away with the equal by keys and values. So what this is going to do is make sure that each map has the same keys, the same set of keys, and then for each key, they map to the same value. So there's no worry about sorting, no worrying about compare doubles. So I actually do get away with equal here. Even though it's a pretty complex comparison, there's a lot going on right here. I actually do get away with this one. But of course, I do fail my code because my code just returns the empty map. So empty map did not equal what I expected to be on this input. This is my hint text, is this input here. So let's implement this method. So here, I'm going to have to, maybe not have to. I think I could do it without, but I'm not going to because I want to give an example. But we almost have to use recursion here. So, and I'm certainly going to use recursion. Let's get most frequent out of the way. Hopefully we do get to that one. And I'm going to pull up my 4 ingredients for successful recursion and make sure that we hit all 4 of those ingredients. So first, I want to start with a trivial input-output behavior. I'm going to start with that base case. So I'm going to do them a little out of order than I introduced them in the slides. But I'm going to start with the base case. What's a good base case here? The thing's empty. So if I'm given an empty list and asked to generate a histogram, here you go. It's an empty map. Base case done. So we have our base case, and now we want to assume that any recursive call is going to be correct, build our logic around that assumption, and make sure all of our recursive calls get closer to the base case. We're down to our 3 other ingredients, our 3 recursive step ingredients. So for that, I'm going to assume that any recursive call is going to be correct. So somewhere in here, I'm going to have a recursive call. If I don't have a recursive call, I'm going to have a loop, and that loop is going to have some accumulator variable, and once we have a variable, well, we're screwed, because we're not doing variables in LO3. So I'm going to have some recursive call, and I want to get closer to the base case and then build my logic around the assumption that it's going to be correct. So what I'm going to do, and what's common in recursive calls like this, is just try to make the input incrementally closer to the base case. So what's the simplest thing that I can do to get this closer to the base case? That's what's going through my mind when I'm writing a recursive method. So the very simplest thing that I can get that's closer to the base case is just remove one element from the list. So I'm going to remove the first element from the list and make my recursive call with that. I'm going to assume that this gives me the right answer. I'll call it smaller answer, or smaller histogram. So I'm going to assume that this is, in fact, the histogram, the correct histogram for all of the values in this list, except the first element. I assume that's true, and if my other 3 steps of my other 3 ingredients to this recursion are in there, then that will be true. So I'm going to assume this is true, and if I have this histogram for all the n-1 later elements, all I have to do is process one element, the first element of this list, this data.head, the very first element. If I process that and add the information from that one to this histogram, then I'm good to go. So how am I going to do that? Well, there's going to be two scenarios here. So either if, smaller histogram I called it, if smaller histogram dot contains data.head. So I got two different situations. Either I've already seen this value before and I need to update my histogram, or I've never seen this value before and I need to add it to my histogram. They're two different scenarios we have to handle independently. This is going to come up, this exact situation will come up in lecture task 4 when you're processing the songs. Either you're finding a song for the first time and you need to process that song for the very first time, or you've seen this song before and you need to take those new ratings and add them to the existing song object, which is immutable, so you have to create a new song object and process it that way. So we have this decision. Have I seen this before and I add it to my data structure, update my data structure, or have I seen it for the first time and I need to add it to my data structure? So if I need to, I'm going to do the add it to my data structure first. So if I need to add it to my data structure, I'm going to do smaller histogram plus a new key value pair, which is data.head. You know what, let me name this variable. Element to process? Sure. The element that I'm currently processing to 0. So I'm going to add that key value stored to my histogram. Oops. I've seen it once. So if this is the first time I've seen it, then I'm adding that to my histogram because I've seen it once now. So for example, if I'm given a list, if data is a list with just the value 1, do I have that test case? Bless you. I need the test case of just a single element. Nice little singleton. Then it's going to add that. It's going to take the empty list, or the empty map from the base case, and add the element from the singleton, mapping to 1, and that's our entire histogram. So when we're one step up from the base case, that's our entire histogram, is that singleton. We've just seen this one element, and we've seen it once. On with our days. It's a little more complicated when we have to update the histogram. So here, we're going to update this, the key value store, and we're just going to add the key value store that we want to add, and it'll overwrite whatever old value was at that key. We can't have duplicate keys in a map, so if we add a key value store with a key that's already in the histogram, in the map, then it's going to overwrite whatever was there, whatever key value store was there. So I'm going to add a key value store, mapping this element to the value that I want, and the value that I want is pulling the element from the histogram and adding 1 to it. So I'm going to ask the histogram, hey, how many times have you seen this element before? It's going to tell me that's what this is. I'm going to add 1 to it. I'm going to map that element to this new updated value. Equals plus. To that new updated value, I'm going to add that key value store to the existing map. And then since this and this, these are the last statements that are executed, one of those two will be the last statement executed. That's what I'm returning. So I'm going to return the histogram with all n-1 elements processed, assume that's correct, and then I'm going to either update a key value store or add a key value store to say that, hey, I've seen this one element one time or one additional time. So I'd say we got all four ingredients to our successful recursion. I'd say we're pretty solid on this. Does anyone agree, disagree? It doesn't matter because we have a nice test suite. We're just going to run the test suite. If the test suite says it's good, we're going to say it's good. We don't have to guess and ask questions and trace through the code, and we're done with that stuff. That stuff, we left that behind in 115. We wrote a test suite. I'm going to go to my test suite and check, is it good on all of these inputs? If it's good on all of those inputs, I'm feeling pretty good about it. If you look at your test suite and say, if any code passed all of those inputs, I'm still not sure. I'm still not sure if it's correct. If that's what you say when you look at your test suite, add more test cases. Convince yourself. Write a test suite that's good enough to convince yourself that any code that passes the test suite doesn't have any bugs. That's correct. So let's run this guy. I'm pretty confident. I think it's going to green bar. And we got our green check mark. So we're good. One thing I like to do, just because I get a little crazy with things, I like to break my code and then watch my test suite fail just to verify that it is testing something. So now I have broken code, my test suite failed. I'm feeling good about it now. Mapping got 1 to 0, expected 1 to 1. Cool. I'm feeling good. Fix my code, run it. So I know I'm actually testing something. One thing, like you get the green bar, you're excited, your code's good, and then you realize you forgot to add any asserts into your test case. I've done it before. We've all been there. And it just passes everything. You submit to Autolab and it says, it passed everything. You didn't fail any incorrect solutions. It's because you didn't add any asserts. It happens. So I'm feeling good about my test suite here. Feeling good about my code because it passes my test suite. If this were a lecture test, I'd be ready to submit to Autolab and get my credit, get my full credit for this thing. Any questions on this guy? Let me go back to the code. Let me show the code and ask if you have questions. We just wrote a successful recursive method. All right, let's move on. I want to try to get through 2 more examples, so let's do this. So numberguesser, I set up a lot of the structure here. Again, I don't want you to sit here watching me fill in boilerplate. So anything that I expect you to have really down solid at this point, I'm just filling in. Compare doubles. Most of the boilerplate here, calling the method. So, let me go to the method first. So this method, just a reminder, is going to take a lower bound and an upper bound and a function. And this function is going to return true if it's given a number where the hidden number is higher than that number, and false otherwise. So false for ties and if it's lower. So this is the hidden number higher than whatever I give it? So we have a case where we're taking in a function here. Then lower bound and upper bound are the bounds. So I'm thinking of a number between 0 and 100. Those would be the bounds. And then we're going to make recursive calls where we update these bounds and narrow down to the correct number. To test this thing, I'm going to call it with the lower and upper bounds and some guessing function based on what the hidden number is. And I want to talk through writing that function because that's still new stuff that I don't expect you to have a complete grasp on. I have a few test cases. I'm thinking of a number between 0 and 100. I'm going to have test cases. I should have left my test cases in here. The test cases, I'm just going to come up with a whole bunch of numbers between 0 and 100. I'm going to make sure I test the endpoints, the midpoint, and then some random values, and a few values out to 2 decimal places. My upper and lower bounds, 0 and 100. And then I'm going to call my method from up here to actually do the checking that we'll talk about in a bit. Let me get my test cases back in. 0.55, sure. 12.83. 0.15. 99.96, etc. So from the problem statement, we said that we should guess the value to 2 decimal places. So I could go out to 3 decimal places or more. It's not going to hurt anything. Actually, it's probably a good test to have. And then since I want to test to 2 decimal places, when I'm doing my compare doubles of the expected values, guess what my epsilon absolutely should be? 0.01. That's going to test, is this accurate within 1 decimal, or within 2 decimal places? 0.01, that's a perfect choice for epsilon. There's really no other good choice for epsilon. I mean, maybe 0.005 if you want to get, you could do some extra logic, and try to figure out what exactly to be. 0.01, perfect choice for epsilon. Checks within 2 decimal places. I have another test case that's going to check for negative numbers. I want to make sure that I'm checking negative numbers and making sure that things are working with large bounds. Negative numbers, I'm going to have a few test cases here. Negative 1,000, better check the endpoints. Sure, a handful of test cases. Enough to make us reasonably assured that we're getting the right answers. We could add more. You know what, I think these test cases are pretty good. Might add one more that's only negative numbers and make sure it's doing good down there in that range as well. And maybe another one that has a very narrow range, like 0 to 1, -5 to -4 or something like that, if I wanted to take more time and make a really thorough test suite. So we're left with coming up with this guessing function. This function should return true if the hidden number is higher than an input guess and false otherwise. So I want to create a function of type double. It's going to take in a double. That's the number that the user is currently guessing. It's going to return a Boolean. So the type is double to Boolean. It's going to take a double. And it's going to return a Boolean based on if the input D is, let me name this something better, the guessed number. This is what the user is guessing. And I want to return true if the hidden number is higher and false otherwise. So here's the trick that we want to do here. This number to guess isn't an input to this function, and we can't hard code it into the function, or else we'd have a separate function for every single one, which I guess we will have. But we can take this variable and put the variable right in here. So we're adding more information into this function by kind of baking in that value into the function itself. So even though the hidden number isn't an input to this function, we can still, at runtime, build a function, generate a new function object that has that number built in and do that dynamically. So we're not hard coding, 15 different functions for each one of our inputs. We're not hard coding these values in here. We're taking a variable and then generating a new function based on the value of that variable, or the value of that value, technically. So I have my function that takes in a double and returns a Boolean. I'm feeling good about my guessing function. Now we can give that function, give the upper and lower bounds in the function, and test this thing using our compare doubles. And then I have a hint text. Because I'm using compare doubles, I won't get nice output from the library, since it's just checking a Boolean. So I'm going to have some hint text to give me a little bit of clue what happens when I do something wrong. We can run this test suite. Oops. And it fails. I might have actually passed the test case. Expected 100, computed 0. And I did pass one test case. I passed the test case of 0, 0. My method accurately guessed 0, 0. Because that's all it returns. So we have our test suite, feeling good about it. Now time to write our code and then run our test suite to see if our code is correct. So I'm going to use a version of binary search here. I'm going to guess the midpoint, ask the function higher or lower, and then my next guess will be the next midpoint, either higher or lower. So what I want to do is a few things. I want to compute the midpoint, which is going to be lower bound plus upper bound over 2.0. So I have the midpoint value. That's the value I want to guess. I'm going to call my function with the midpoint. And if else, so if my next guess, the hidden number is higher than what I guessed, what I can do is eliminate every guess between the lower bound and the midpoint. To do that, our good friend recursion is going to come in. I want to eliminate, so the number I'm looking for is higher than the midpoint. So anything lower bound to midpoint is no longer an option. So my new lower bound, I'm going to call that my midpoint. Upper bound stays the same. We didn't learn anything about that. And then forward the function. If the value is lower, same idea, except everything above the midpoint is gone. I'm just going to keep guessing while narrowing my bounds in on itself. So I have a recursive call. I'm just going to assume that those are correct, that those are going to return the actual hidden number within 2 decimal places. All my logic built around that seems solid, and my recursive calls are getting closer to a base case. How are we feeling about this recursion? Are we missing any of the 4 ingredients? I don't really seem to be doing anything. So we don't have a base case here. And we just hit some infinite recursion. It actually didn't overflow the stack for an important reason, because this is tail recursive. It's something we don't really need to discuss in this class. Actually, I can show you the stack overflow. So this is no longer tail recursive. And we'll get the stack overflow. We should get the stack overflow. Oh, come on, don't make it fool me. Why do I go down these journeys? There we go. There we got our stack overflow. So we hit infinite recursion, we're going to get our stack overflow, unless our tail recursive topic, again, we don't want, I'll talk about it if somebody's interested. I'll happily talk about it. The TLDR is when the recursive call is the last line of the method, the compiler can collapse all the stack frames and not actually add more stack frames, because every stack frame, its purpose is just to return a value. So it just collapses all the stack frames. But we're missing a base case here. So what's our base case going to be for this method? It's going to be when our search space is within 2 decimal places of the answer. So I'm going to say if, assuming the upper bound is higher than the lower bound, if upper bound minus lower bound, if my search space is less than 0.01, then I'm going to call off the search and say, you know what, we're done. And in that case, I'm going to do a little bit extra here. I could return upper bound or lower bound. I know they're both within 2 decimal places of my answer, but I'll get a little fancy with it and return midpoint. Else, everything else. So everything we wrote before was just the recursive step. Now we added a base case, which tells us when to end. And since every time we make a recursive call, we're cutting our search space in half, we're always getting closer to that base case where our search space is 0.01. So it's a little bit different structure, a little bit different thought process than the recursive examples we've seen so far, but we still have the same ideas. Those same 4 ingredients are always going to be true. A base case with trivial input-output behavior, I'm not doing any searching at all. I'm just saying, hey, search space is small enough, return something. Recursive step assumes that these values, these recursive calls will return the right value. They're both getting closer to the base case since they're both reducing the search space. And my logic is sound. I'm going to call the function. And whether the function says higher or lower, I'm going to narrow my search space to not exclude the number that I'm trying to guess. So I got all my 4 ingredients. We can test this thing. I'm feeling pretty good about it. And we're good. I always like to see my test cases fail. So what I'm going to do is just break my base case. Make sure my test is testing something. Expected 0.0, got something that's not within 2 decimals, but pretty close. So I'm still getting close. My algorithm's still working fine. I just didn't have a tight enough bound. Turn that bound, run it again, passes my test. Ready to submit to Autolab, and Autolab's going to be happy with everything I've done here, if this were a lecture task. Any questions on this one? All right. For the last one, I built the test suite already because I knew time would be tight if I even got to this one. So we did get to it. And I want to add a new method that's going to give me the most frequent value or values that are found in a list. I'm just going to fix this. This one I just want to talk about the code mostly. Oh, I'm not even doing, I didn't even call it. I didn't call the right method. What did I name it? Most frequent. We have to sort these because they're lists, et cetera. They're lists that we don't care about the order. But I want to get the most frequent, or the mode, from each of these lists. So here, 2 is the most frequent value. Is my formatting not working? Whatever. So 2 is the most common value, so I'm going to return that. 1 is the most common value, return that. If there are ties, return them all. That's the TLDR of what we're doing here. I want to return the most frequent value, and if there's a tie, return them all. So return a list of the most frequent values. Here we have 3 1s and 3 3s. Return them both. Only 2 2s. 2s don't make the output. So this can seem like an easier answer. This is one, or an easier question. This is one where it's a very deceivingly difficult, like if this were a lecture task, it's very deceivingly difficult. Assuming no var. With vars, it's whatever. It's a little bit of work, but it's not that bad. Without var, this is one where, give me the most frequent value. Is a little trickier because there are a few steps that you need to take to really think about how the answer is going to work. So let's take a look at how this will work. Well, let's run the test suite, I guess. Let's run the test suite. Failed. We know because it just returns an empty list. But if I just gave you most frequent, it's tough. Because there's kind of implicitly in here the need to build a histogram. Now, the way I ordered these, you just call your histogram code that you did from an earlier lecture task, assuming this were like a homework that I was building, a project I was building. We're just going to call that. But if I just told you do the most frequent thing, you might not think, there's an extra step in there. There's a leap to say, what I'm going to need is a histogram. just maybe in LT4, you might want a recursive method that returns a map of, I don't know, maybe YouTube IDs to songs. That's a case where I gave you a question where you're just returning a list, but intermediate processing, you might want to do something else. You might want to write a different recursive method to get data in a format that you can work with, and then do some final processing with that data. So for most frequent, the very first thing I'm going to do, I'm going to grab that histogram. I'm just going to call it histo. It's a map of int to int. And it's going to equal histogram of data. So if you're just given most frequent, you might not think, you know what, I'm going to want to build this histogram. I'm going to introduce a map. Even though map isn't mentioned in the question at all, I really want to work with a map that's representing a histogram of this data. So I'm going to call histogram, take advantage of the fact that I have this code that's written, it's tested, I submitted to Autolab, Autolab said it's good. I'm going to take advantage of that and say, I'm going to reuse that code and just grab the histogram and then start with this histogram. Now writing the code isn't as bad. There's still some tricks. This is where we think about last Wednesday, all of the ways we can work with data structures using functional programming. So I have this histogram, and I'm going to do a few tricks here. This one might be a little much. How much time? 3 minutes? Yeah, let's do this. Data dot distinct. I'm going to get the distinct values. I'm going to get the max value from the histogram. So I'm going to get the the values of the histogram, get the maximum value. I'm just going to hit it with a dot max. So now I have the distinct elements. I'm going to call these, I have time to name this. My candidates for the maximum, the most frequent value. Candidates? Is that really spelled wrong? When you can't spell, just read please. So I have my maximum value that I'm looking for, and I have the potential options, and we have a filter method, which is going to take a function that's going to filter out the values that I want. So if my filter returns true, that means I want that value. So for each option, I'm going to check, does histo of that option equal max? I'm going to run my tests. And we green barred. That passes. This gives me the distinct elements. Just for those of you who really want to see some coding. Oh, that last one would be pretty bad. When I say, you know what, I'm doing it just... No, that gets too bad. I can't do that next one. It's just so inefficient to do the next one. But with functional programming, we can get our code really compact for better or worse. You know, this is probably a bit harder to read. But I'm going to take the data, take the distinct values from it, and filter them based on if that histogram value is the maximum value from the histogram. It almost reads like an English sentence, much more so than like a loop with the old accumulator pattern. But it can, you know, there's a lot of steps in here where you can lose somebody. You can lose one of your devs that's trying to read this stuff. So I'm going to not do that and split it into a few separate lines at least to be able to get those distinct elements, those maximum elements, sorry, not distinct elements, the maximum most occurring elements. Then I'm going to push this to the repo. So you can see these examples. These are in, by the way, a live coding directory, which is right alongside all the LOs. So that live coding directory is where I put all these things. Push anyway, push. So if you're interested in those examples and looking through them. All right, have a great weekend. I'll see everyone Monday.